Hello, everybody, and welcome to Chapter 5. So now we are talking about chemical quantities and an introduction to chemical reactions. So we've built a nice progression here from talking about matter and what matter is and composition of matter to elements and atoms. Elements and atoms combine to make compounds, and now compounds can change in chemical reactions. So now we're going to be looking at chemical changes in matter. So that would be a certain element and or compounds transforming and turning into different elements or compounds. That's like a simple definition of a chemical reaction. One thing turning into something else. And this happens by breaking existing bonds and forming new bonds. So we will see eventually that um, the idea of like matter is neither created nor destroyed, like the same number of atoms of the same type of atoms and everything is still there, let's say in your beaker, but now it's going to be arranged in a new way. The bonds that were there are broken and new bonds are formed in a new way. That's basically a chemical reaction. Okay, so the first section is about counting and weighing matter. And this will introduce a concept called the mole. But first, let's think about what matter is and what kind of scale we humans live in, right? Atoms, ions, molecules are extremely small, right? You can't actually count like 5 atoms out very easily, right? But because they're so small and the world that we live in and that we observe is very large, right? We're going to be dealing with massive numbers of atoms, ions, and molecules interacting in chemical reactions. And so instead of trying to count individual uh, atoms, molecules, for example, we can calculate the mass of a large number of these units using the formula mass, molecular formulas. And then we can make quantitative relationships between the number of particles that we have and the mass of a sample, right? I'll give you more examples of this as we go through. But the idea is that we know atoms, ions, and molecules undergo reactions in whole number proportions, right? You can't have half of an atom, you can't have half of an ion, or a quarter of a molecule. So the number of atoms is an integer, it's a counting number. It's just a really, really big number, and they're really, really small. So we're going to introduce molecular mass as a concept. So the molecular mass of something like, say, water can be determined from the periodic table. Water is H2O, right? We know a lot about water by now. We know the Lewis structure, the shape, that it's bent. We know that it's polar. We know that it would have hydrogen bonding, intermolecular forces. So we know a lot about water. And now we want to add one more thing, which is how much does a water molecule weigh? What's the mass of a water molecule? Well, we know from the formula that it has 2 hydrogen atoms, and the periodic table says hydrogen has an average atomic mass of 1.008. So remember, it's not exactly 1 because we have um, isotopes, right? So it's 1.008. And so those 2 hydrogen atoms would give a total of 2.016 atomic mass units. So AMU is an atomic mass unit. You may remember this from previous chapters. And so it's intended to kind of make these numbers simple and nice. So basically 2 hydrogens are 2 AMU, and then 1 oxygen from the periodic table has atomic mass of 16.00. So that's going to be added to the 2.016 from before, and we get 18 38.02 atomic mass units per molecule of water, right? And every water molecule is exactly the same because every electron, every proton, every neutron is identical to every electron, every proton, and every neutron. And so a water molecule is always 18.02 AMU per molecule. Just for a little more practice, let's look at an ionic compound, right? This is ionic, magnesium chloride. So same idea, 1 Mg 24.31 Cl, there's two of them at 35.45 each. So it's 70.90 AMU, and the overall ionic formula unit gives 95.21 atomic mass units, right? So it's simply like adding up the masses of each of the atom gives us the total mass of the molecule or the compound. Here's another example. So go ahead and work this on your own. Find the molecular mass of glucose, sugar, C6H12O6. So pause and try this. Okay, and welcome back. So you maybe possibly set up a table like we did before, and you can see the different types of atoms, how many, the atomic mass per atom, and then the total. Do that for each type of atom and add them up. And so we get the glucose has 180.16 atomic mass units per molecule. Okay, now once again, molecules and compounds are very small, and often we have a very, very large number of them. So now we're going to think about if we know, here's where we're going, right? Think about this. If you know the mass of a molecule, and now you have a big sample, and you can take the mass of your sample, can you figure out how many molecules you have? Right? If you know the mass of each molecule, you know the total mass of your sample, you can figure out how many molecules you have. All right. One more step as before we get there is an analogy to make sense of this from a different context. So this section is called Counting and Weighing Matter, the mole. And here's your analogy, counting and weighing nails, the dozen. So say that, well, of course, not say that, but nails do come in whole number amounts, right? If you want a nail, you want 1, 2, 10, 20 nails, not half a nail. Well, some hardware stores sell nails by the pound, which is easier than selling them by the nail because customers often need hundreds or more of nails, and counting them takes too long. So you just take the mass and determine it that way. So suppose that a dozen nails of medium size weighs 0.150 pounds. You, the customer, go in and you buy 2.6 pounds of medium-sized nails. How many nails did you buy? So this is like the exact same problem that we're going to face with molecules, mass, moles, but it's different context. So let's do this first, and we'll see if we can make some sense of it. So there's two conversions that we're going to need, right? One is between pounds and dozens, and one is between dozens and number of nails. Right, so here's the first one. A dozen nails weighs 0.150 pounds. And then number two is not actually given in the problem, but you know this one, right? If you have a dozen nails, how many nails do you have? If you have 2 dozen, how many nails? If you have 1.5 dozen, how many nails? Right, this is a conversion factor. It says 1 dozen equals 12 nails. And so we can simply write conversion factor, either way, by taking a ratio. And of course, nails here can be replaced with anything because dozen, by definition, means 12, anything, right? So we can now think about how we would solve this problem where we start with a known measured quantity, which is the mass of mass of nails, right? And then we're going to take conversion factors until we get to the number of nails. So something like this as a unit plan. So given nails, we can then use a conversion factor. Remember, each arrow counts as a conversion factor to give us dozens. And then from dozens, we can get number of nails. So let's actually, I don't think I left myself enough room here. Let's actually try this though. I can find some room at the bottom. So I have 2.60 pounds of nails. I'm going to multiply by 1 dozen by the the mass of a dozen, right? That cancels out pounds and gives me dozens. And now I know that I have 12 nails per dozen. And so pounds cancels out, dozens cancels out, and I get nails. And calculating through, we get 2,080 nails. All right. So there we go, right? And if we look at, let me duplicate this here, get rid of that stuff. Okay, so we're looking at these conversion factors here. And the first one, between the pounds of nails and a dozen, depends on the problem, right? If we had large nails, this would be a different number. If we had small nails, it'd be a different number. But a dozen is equal to 12 nails. That never changes. That's always true. That's the definition of a dozen. So half of this problem is already set for us in dozens. The other one depends on the problem, and it has to be given, or somehow you have to be able to find the information. Okay, so with this in mind, we're going to basically do the exact same type of problem, except looking at molecules, and instead of dozens, we're going to look at moles. Okay, now the mole is a very famous chemistry thing, and for some reason, a lot of students get mixed up with moles. And I want to convince you that if you can understand a dozen and what that means and how to talk about 1 dozen, half a dozen, and so on, then you can understand a mole. It's just a number that represents a counting unit. It happens to be a big, strange number, 6.02 times 10 to the 23. But it's just like the concept of a dozen. There are other examples here, right? If I say a pair of things, like electrons, we talked about that before, a pair of electrons always just means you have 2. If you have 2 pairs, then you have 2 times 2, you have 4. A case, 24 case of something, whatever it might be, you have 24. If you are celebrating, you have 2 cases or something, and then you have 48, and so on. So these are all examples, and a mole just fits right here. So these are just conversion factors between the counting unit and the number of things. Remember, the goal is actually to make your life easier, right? So instead of having to count big numbers, you can talk about dozens or talk about moles. And we can always write a conversion factor by taking the equal sign and making ratios out of these. And either ratio is perfectly acceptable, just depending on what conversion you're trying to do. So if 1 dozen is 12 things, it's just like saying 1 mole is 6.02 times 10 to the 23 things. And if you have 6.02 times 10 to the 23 things, you have 1 mole. All right? Well, let's pause here and we'll come back for part 2 and continue talking now about the mole.